So in principle, one can probably improve this bound and push it further up. And ideally, the hope would be to close the gap somehow. And so this is for the upper bound. And
is there something special about the initial region? Like both curves, down curve, I mean, it comes down like this. Is there some reason that do you expect that the actual bound will be always has this kind of feature that less than 0.75 has some?
Oh, I see. So yeah, that's true, because so it comes from the, at least I can see it from the way we have done it, that for large enough delta things go down because because some optimization thing. And so the point is, how do I say? So the point is, for large enough delta there is less room for improvement. Like I guess I don't have any physical picture of it, but from the analysis it's very clear that it should happen, like it should go down.
Do you think they actually function these things?
It might. So there's no, it might be like this random function, but like there's no guarantee that it would be as smooth curve or something.
Does it decrease with delta?
I think it should decrease with delta, yeah. Like it should decrease with delta, but after some delta it should be flat. But initially there should be a decrease. At least that is clear from the way we figured it out. But then after some cutoff delta it should be a flat. So you can see there is a flat line here. Also in there is a flat line here in their analysis also. So now we go to the lower bound. So again the blue line is their lower bound, and then we improve it a little bit for delta greater than, this is like 0.9 or something like that. And you can see there is a discontinuity here, because, and this discontinuity appears because this improvement happened to an entirely different function which came from the sphere packing problem. And I should thank John, because John told me to look at the sphere packing paper. And so that function did not appear in that sphere packing paper, but I traced back. Then in 2004 a sphere packing paper appeared where they were talking about the sphere packing in one dimension, which is the trivial one. And in one dimension some function, one can write down a function which actually saturates the bound, and this same function actually improves our bound. And then also we do the bound on the upper bound on the lower bound, where again we have a green line which is the analytical bound, and then we do numerics and we can improve the green line up to this point, and this whole shaded region is not allowed. So here also the optimal bound lies like this, and here also you can see the similar pattern, like it's going up instead of going down. So these are the two important results from our paper. And then if we move, and then before going on, so because we have some results, so we proved a theorem and this result should hold, but as a physicist you always take up some models and verify it. So here are the verifications. And so again you take 2D Ising model, you figure out the actual density of states and the actual entropy associated with different little deltas. So delta like I take 0.875, 1, 1.7, 0.75. And these blue lines are the numbers coming from the actual Ising model. The black line is the upper bound and the red line is the lower bound. And you can see that every time it lies within these bounds, well within the bounds. And ideally the bound is supposed to hold for asymptotic deltas, but amazingly for 2D Ising model, like delta equals 100 is large enough delta. So it works really good for, at least for 2D Ising model. And another curious feature is, which I haven't figured out why, like for every integer delta, the error is really, really less. And this pattern actually survives for 2D Ising model, monster CFT, and k equals 2 extrema CFT, everything. Whenever delta is an integer multiple of 1, then the error is really, really small. Like, you can compare all these values.
This is for effect of descendants.
It might be, but I have a feeling, but I haven't. So you know about this partition of an integer where you have this Rademacher formula, which is a more precise formula of a partition of an integer, and there you can do it because you know exactly in which positions the operator sits. Like, it's the integer, right? So I guess here also a similar kind of thing happens because there are descendants sitting at a one apart. Maybe you can write down a Rademacher like formula and do much better. Like, that's the hope. I don't know. So yeah. But the pattern is there for Ising model, monster CFT, k equals to everyone. Whenever this is a multiple of 1, the goes like this. Okay. So this is for the monster CFT. Like, these three are for the monster, and this is for k equals to extrema. So here you can see the asymptotic feature of the bound. So for low enough deltas, the bound is not really satisfied. But as you tune and go to large enough delta, this whole band goes within this upper, the black line and the red line, and the bound is satisfied. Okay, so we have these verification plots, and now I come to the last part. So can you say something about the spectral gap in CFT? So the idea is here we have some lower bound on the density of states or entropy, right? So if I can show that for a fixed little delta, for all capital delta greater than some cutoff delta star, if this equation holds where we need a strict inequality here, then the spectral graph is bounded by 2 delta because there has to be like states within this window to make this happen. So just by choosing different delta, and if we can show there is a strict inequality, I can prove some bound. Yeah, there are two major things. So it's like you can think of this. So suppose you show that this is greater than 0 for some energy window, and that means in contradiction, suppose there are 2 states which are apart from more than that. So you can take the window within that region, and then that will be contradiction to the inequality, right?
Yeah, no states in between.
Yeah. So that means the gap has to be less than 2.
So if I spectral graph, you mean the smallest space in between any 2 states?
Yeah, it's bounded. Yeah, right.
That's what you mean by spectral graph.
Yeah, at this point it is any 2 states, but again one can do everything sensitive. One can make everything sensitive to Virasoro primaries, and then
But in general, a rational state too, can't you have? Can't they be arbitrary reports?
so it's bounded above by 2 delta. They can be arbitrary.
Above. Oh, okay.
Yeah. So basically the Russian paper, the MZ showed that 2 delta is 1.1 with this particular number. And then they conjectured that it should be 1. And the reason behind their conjecture was monster CFT, where all the operators are separated by 1. And we actually showed that 2 delta is exactly 1. So we proved their conjecture. And so the way I have shown you, this shows that this is for all the states, but then one has to do a little bit of extra, and then, like as I was mentioning, for central charge greater than 1, the analysis can be made sensitive to the Virasoro primary zone. So this also then means that the asymptotic spectral graph between Virasoro primaries is exactly 1. And in normal case, it is trivially satisfied by the descendants because they are 1 apart. So this, like both of these results are non-trivial in case of C greater than 1. And one cannot improve it because it's optimal, and there is an example. So this is the best result we can have.
geometry to your sort of primary is only.
Yeah.
And it's a trivially small. Because,
It's a
you know,
trivial result because you know there are descendants. Yeah.
So,
Yeah. And so now I will briefly say about some, like the techniques we use. So at this point, this will be really sketchy. Like you can ask me later what are the exact details. I can spend time, like because I am really excited about this. So the roughly like you arrive at some inequalities like this, where you estimate the density of states by some upper bound and lower bound, where this rho 0 is the Cardiac approximation, and this C plus and C minus is defined as some integral over the indicator function. Sorry, integral over some phi plus and phi minus, and this phi plus and phi minus are some band limited function which approximates the indicator function from above and below. And to give you a hint why the indicator function is important, so you can think of this integral as an integral of from 0 to infinity rho of delta prime times the indicator function for this interval, right? Because that cuts off the integral between this region. And once you have the indicator function, then you approximate the indicator function by this phi plus and phi minus, which are band limited. And the reason we want to have a band limited function is we want to have a situation where the error term becomes very small, and most of the error terms comes from the heavy states of a partition function. So if I have an indicator function, the Fourier transform of the indicator function will be sinc, and sinc has a like infinite support. On the other hand, if I use phi plus and phi minus, it will have a finite Fourier support, and that means like lot of contribution coming from the partition function can be easily neglected. So that's roughly the idea of why you are using the phi plus phi minus band limit.
Would it work just as well to use a low pass function? I mean, a function which is only limited, which only excluded 5
No, because you also want on this side, right?
but the density states vanishes eventually low enough argument.
Maybe.
Increase the power.
Yeah, maybe. Maybe, but then I'm not. Yeah, it might work actually. So most of our result follows from some choice of band limited functions. And I said artistic, but it's basically like going through a lot of bad choice and gaining some intuition about the good ones and coming up with the good ones. So and also these band limited functions are the ones which are useful for the ECE people in the information transmission, and that's where my friend came in. He is over there, Shobit. So